We've got another video now. This is from the Institute of Physics. In fact, Nicky Thomas, who's been helping me here all day, answering, as you've seen, questions on the panel and also on the Facebook feed, I think, has actually contributed with a series of experiments in this video as well. So thank you, Nicky, for doing that.
Hello, so this is Nicky Thomas from Institute of Physics, and I'm standing in the bandstand at Malvern Priory Park, just recording a lovely way for you to remember the spacing of the planets in the solar system. So imagine I've got the sun on the top of my head, and Pluto, we're going to pretend Pluto is still a planet for the purposes of this exercise. Pluto right at my feet. So how are those planets spaced? Well, I've got the sun, I've got Pluto. On my knees I've got Neptune. On my hips I've got Uranus. My armpits I've got Saturn. My chin I've got Jupiter. My eyes, that's Mars. And then squashed between, the last little bit from my eyes up to the top of my head, that's Earth, Venus and Mercury. So really, really closely squashed together. So I've got the Sun, Mercury, Earth, Venus, Mars at my eyes, Jupiter on my chin, Saturn at my armpits, Uranus at my hips, Neptune on my knees, and right at my feet I've got Pluto. It's a nice easy way to remember what order the planets are in and where they are. I'm going to compare the different sizes of our planets using balls. So if Earth is the size of a tennis ball, then how big are the other planets? Well, Venus is also the same size, roughly. Mercury, which is the planet closest to the Sun, is quite a bit smaller. And Mars, our closest planet, is also quite a bit smaller. These four planets are called the rocky planets. When we move further out, we come to the gas giants. So the first planet we come to is Jupiter, which is the largest planet in the solar system. Then we have Saturn, then we have Uranus, and then we have Neptune. And finally, on the end, we have Pluto. Pluto is about the size of a marble on this scale, and I still count Pluto as one of our planets, although we would strictly speaking call it a dwarf planet now, as there are other planets a similar size also in our solar system. Is starlight safe? Well, it's very intense once we leave the Earth's atmosphere. So we need to protect astronauts against very intense radiation. So I'll just look at ultraviolet and infrared. Ultraviolet radiation can cause skin cancer and sunburn. So when the astronaut's looking out of their visor, what would be the best colour for that visor to be? So I've got three filters here. I've got a clear, a yellow and a blue. And I've got these beads which will change colour if they absorb ultraviolet, which means if the filter has allowed ultraviolet to shine through. And I'm going to put it underneath my ultraviolet light, leave it there just for a few seconds, and let's see whether one of those filters is better at absorbing the ultraviolet light so it does not allow it to reach the beads underneath. So I think we can probably have a look now. As you can see, the clear filters allowed lots of ultraviolet through, so we've got a big colour change. The yellow filter allowed some through, so we still got a colour change, but that blue filter would be a bit tricky to look through, but it certainly would be quite effective at absorbing the ultraviolet light. How about infrared? Now, infrared radiation will vary because of the very extreme temperature changes that the astronaut could be exposed to. So I'm just going to do a quick experiment using this thermochromic paper, so it will change colour if it warms up. So you can see where I put my fingers just there on the edges. So what colour should the spacesuit be? Well, we want it to reflect a lot of heat. I'm going to use the lamp as my heat source, and I've got two pieces of foam, white and black. I'll place them on top of my thermochromic paper, and I'm going to turn my light on. So what we're looking for is as small a temperature change as possible. We don't want our paper to change colour, because if it changes colour, that means that we've allowed the heat through, and so our poor astronaut could end up getting very hot or very cold. So let's see. I've got black and I've got white. And as you can see, where the white foam was, there's been much smaller temperature change. That colour hasn't changed much. Where the black foam was, we've had quite a big colour change. So let's make the suit a nice white shiny colour to reflect the infrared or radiation. No, your eyes have not gone funny. I put something called diffraction grating in front of the camera. Diffraction grating splits light into the different colours that are present coming from the light source. And this is how we study stars. The light from the stars shines through different diffraction gratings. We can identify what colours of light are there, and those are a sort of unique fingerprint to different elements like hydrogen and helium. I'll just demonstrate how things look different with different light bulbs. What you're seeing there is the light coming from a normal filament bulb, so you've got all colours of light in that spectrum. Here we have a fluorescent light, and you can see, one of those energy efficient bulbs, you can see very discrete colours. And here we have an LED, and you've got much sharper colours again. And this is because light's produced different ways in each of these bulbs. So can you do anything at home? But you can do this experiment safely if you hold just a normal CD or DVD towards your light source. So what I have here is my LED, and when I'm shining, hold my light source, just angle it. You've got to just kind of be slightly careful how you angle it. And what you can see are very clear lines, but only the colours that are present from the LED. If I repeat it with my fluorescent bulb, again you can see those colours, and they're unique to that type of bulb. And you've got a bigger range of colours here from the filament bulb because there's a bigger number of much wider frequencies of light that are available, many more colours. So have a go, but please don't look direct at the light sources. How do we know what the moon rocks are made of, or meteorites? The answer is we cut very, very, very thin sheets of each type of rock, and we shine light through them. I've got some rock samples here. They're not meteorites though, and you can see that my fingers behind them because these rocks are so thin. And the light will travel through the crystals, and it actually twists a little bit. Different colours of light twist by different amounts. If I put a piece of Polaroid filter, which only allows light vibrating in certain directions, behind the rock crystal, and I take a second piece and put it in front, it'll only show certain colours of light through different crystals, so I'll be able to see that structure. So I've got this for the two rock crystals, and what you'll also see, just to make the effect a bit more obvious, are some pieces of sellotape, because they also act a little bit like the crystals of light, and they only blocks that allow certain colours through. So let's have a look then. So what you can see, if it's bright enough, are the different colours of the crystal here. And then when I twist, can you see those colours changing, particularly pronounced on the top piece of crystal? And then when I twist again, you can see, particularly with the sellotape, but also with the rock crystals, how those colours are changing. And so that's how scientists can study the structure of the rocks. What skills do you need to become a space scientist? Imagine that you're working with samples that have been taken from comets. We don't want these samples to get contaminated, so they put them in a sealed container and they will work using these remote gloves. I'm just going to show you how to make a simple box that can help you practice these skills. I've just got a simple cardboard box, cut 2 holes in the side. I've just put washing up gloves in, tapes around the edges. I'll take this lid off so you can see a little bit better. That's just a bit of cling film. And now inside, what have I got? Well, I've got things like a ruler, I've got rocks, I've got bowls. Oh, you might not be able to see it. I actually found it really hard once I got my hands in. Oh, things like clothes pegs or bulldog clips. Perhaps you could put a screw top jar in or a magnifying glass. And just sort of see how easy it is for you to manoeuvre and do your experiments remotely inside the box when your two hands are stuck on either side, and you can move within the box, but you can't actually move very far. So practice those skills, and let's see you at our space school.